It's my great pleasure to introduce the winners of the 2014 Kavli Prize for Astrophysics, Alexei Sarabinsky, Andrei Linda, and Alan Guth. Now, Alan, I want to start with you by asking you a seemingly simple question, but there are never any simple questions in cosmology. What was wrong with the Big Bang in the 1970s?
Okay, a few things, all of which had to do with the initial conditions for the Big Bang. If you're willing to just accept the initial conditions that the theory needed, there wasn't really a problem. But there were basically two features of these initial conditions that were hard to understand and had to be really precisely right for the theory to work. One of them was the expansion rate of the early universe. If one thinks about the early universe at 1 second after the instant of creation, in the context of this traditional Big Bang theory, that had to be just right to 15 decimal places, or else it would not work. If it were just a little bit faster by 1 digit in the 15th place, the universe would have flown apart without any chance for galaxies to form or life to form. And if it were just a little bit slower by just 1 unit in the 15th decimal place, the universe would have rapidly recollapsed before life could have formed. And there was nothing in the theory that caused it to expand at just the right rate. We just had to assume that that's how it started for some reason. So that's one problem.
It goes from a singularity to the entire universe in the space of what time period are we talking here?
Well, we could be talking about any time period, actually. If we're talking about inflation,
yeah.
Which I wasn't yet,
okay.
That has sort of a well-defined, more or less well-defined time period. It could really start arbitrarily early, and we don't really know how old the universe is, but there's sort of a time that we call nominally time zero. And inflation starts about 10 to the minus 37 seconds after that, and continues for about another 10 to the minus 35 seconds.
Okay, so that was the first problem you just described this is going back, what,
yes.
40 years now. Some of the other issues that set all three of you on the path to, this theory of cosmic inflation, which is why we're here today. What were some of the other problems?
Yeah, the other main problem was the uniformity of the universe. If we look around the universe today, the clearest evidence for that uniformity is seen in the cosmic background radiation. Astronomers have now measured that radiation to extraordinary precision, and it's the same intensity in all directions to an accuracy of about 1 part in 100,000. So clearly all the different parts of the universe knew about each other and knew how to be at the same temperature at the same time. But in the conventional Big Bang theory, there wasn't enough time for that communication to be established. If we trace a photon backwards to its origin coming from one direction in the sky and a corresponding photon coming from the other direction in the sky, in the context of this conventional Big Bang theory before inflation, the origins of those two photons were separated from each other by about 100 times the distance that light could have traveled up until that time. So within the context of that conventional Big Bang theory, we don't see any way how that photon knew how to be at the same temperature as that photon at the same time, yet somehow it happened, and happened to an accuracy of 1 part in 100,000. So that was a very basic problem.
So the universe is, and this is theoretical, or this is based on observations back in the 1970s?
Well, we had observations as uniform today. What that means about the early universe was theoretical.
Okay, so that takes us back 40 years. Now, Alexei, you were working in the then Soviet Union at this point, presumably addressing the same questions that Alan's just described.
Well, the question was the same, but I had a different. I had a different approach, and I think this difference was mainly due to the difference of our origin, I would say. While Alan and Andrei came to cosmology, came to studying the cosmology of the universe from the field of field theory and elementary particle physics. I came it and actually due to my teacher, the great scientist Yakov Hildovich. I came it from the point of view of astronomy, observational astronomy, and so from the point of observational astronomy, where I would say that the main deficiency of the old Big Bang theory was just absence of well, just the absence of the absence of the explanation of initial conditions for the universe, and as a result, from theoretical cosmology, we had no predictions for astronomers to what should they measure, and if measured, what will be the theoretical consequences of this fit, of all this, and what is actually resulted from the theory of inflation. That we really made some definite predictions, and it greatly affects all the development of observational astronomy. After that, it really very fantastically accurate measurements were made, and they actually confirmed our main predictions. So really, as astronomers got a possibility to make not simple measurements, not simply discover one more galaxy, say, but really made as fundamental experiments as was elementary particle physics connected with the prediction, and finally connected, say, with the prediction of the Higgs boson. And finally, after large work, after almost 50-year works, it has been discovered. So over the same time, we obtained a possibility to make some definite prediction, relating actual observations to something very fundamental, which occurred, as Alan said, in the very early part, in the very remote part of our universe, and at very high space-time curvatures.
Alan, how did you came up with this idea at the same time, approximately, as Alexei, this idea which you've referred to as is called inflation? So how did inflation, how does it get around the problems that we've just been describing?
Sure. Inflation is a period of exponential expansion in the early universe, which is driven by something which we think we understand. If we combine general relativity with ideas from particle physics, we discover that there's a real prediction that there ought to be states of matter at very high energies which literally turn gravity on its head and cause gravity to become repulsive. And that's the mechanism behind inflation. So the scenario is that the universe starts somehow. I think we don't really know how the universe started. But then at least a small patch of that initial space we hypothesized was filled with this peculiar kind of material creating repulsive gravity. And then that patch grows exponentially and becomes the universe that we see, and perhaps much more as well. So it gets around this problem about the fine-tuning of the expansion rate, because in the conventional Big Bang, the expansion rate just was whatever it was. We had no explanation of where the expansion came from. But here we have an explanation of where the expansion comes from. It comes from this repulsive gravity force. And we can calculate what it does, and it produces exactly the right rate of expansion to match what we thought the Big Bang needed.
So, Alan, you came up with this idea of cosmic inflation at approximately the same time as Alexei did in the Soviet Union, but because, and I think this is very culturally interesting, because the Soviet Union was relatively isolated at that time, you weren't aware of it. How did you become aware of the fact that the same idea had emerged somewhere else?
That's a good question. I actually don't remember the first time I heard about Alexei's work. I certainly heard about it pretty early, but I have to confess I don't know exactly when.
But this is around about the end of the 70s. The papers are beginning
Early
to emerge
80s.
At the beginning of the 80s. Now, Andre, how did you enter this field? How did you enter the conversation about inflation?
For example, the issues which were studied by Alan, they were based on the theory of cosmological phase transitions. And this is something which my teacher David Kirchnitz and I were doing from the beginning of 70s. So the theory of cosmological phase transitions and energy transition from decay of heavy vacuum state, this is the one which gives rise to inflation. This was contained in our papers. We just did not know whether there is any serious use for that. Okay, in fact, we have found the problems with the exponential expansion in the mechanism which we studied before, and so we didn't do much about that. And after that, Alan came with essentially very similar ideas, but he said that let's use it for something and let's use it for solving different cosmological problems. But then he found also the same problems with which we met. So the idea why we need to do it was there in his work. The question how actually we can do everything fully consistently, that was not clear. So since I knew all of these dynamics of cosmological phase transitions, I found one regime where everything worked, and that was pretty difficult thing. And then after that, about a year later, I found that all of these cosmological phase transitions, they're actually not necessary. So there were two places in my involvement in this which were substantial. The first is how to improve what was proposed, but well, had these flaws. And the second was how actually totally forget about these cosmological phase transitions and do something simpler which works from the very beginning. In particular, for example, Alan mentioned that this regime of exponential expansion in some particular vacuum state, it starts maybe from the time 10 to the minus 36, 37 seconds after the Big Bang. So what was possible to do when we moved further is, well, explaining how you can survive until this big time from my perspective, and we can start inflation from the something which is called Planckian time. You cannot go any further back in time. That's 10 to the minus 43 seconds. So this is the whole million times earlier than what was in the old and the new inflation. That's a called chaotic inflation scenario.
And how is the whole concept, the whole idea received by the community at the time? I mean, it's quite a, it does explain some of the problems, the horizon problem that you just described, but it's also quite, you know, presumably was quite revolutionary. Yeah,
I remember how first it all started from the Russian perspective when Alyosha published his paper, and there was a wave of enthusiasm at all conferences in the Soviet Union. His work was discussed and debated, etc. Then, of course, Alan paper appeared, and I learned about this paper in a very strange way. Somebody called me and said, do you know that Alan suggested a way to solve these all cosmological problems by expansion? And I said, yeah, well, no, actually, I do not know anything about this paper, but let me explain how it is possible to do it and why it does not work. Okay, so all of this we learned about each other in a paradoxical way. So this still continued for quite a while all of this model progressed. I remember how when I suggested improvement of Alan's idea, Stephen Hawking was at my talk, and next day in the morning he gave a talk at Sternberg Institute, which is a part of Moscow University, and I was asked to translate. And he said first why it is difficult to improve his model, actually impossible. Then, and I translated, and I was making most of the talk because he was talking slowly, and I was explaining, knew it. And then in the middle of the talk, he said, "But Andrei Linde suggested how we improve it," and I happily translated. And after that, he said, "But this is totally wrong," and started explaining everybody. And for half an hour, I translated for all the world why my work does not work. And I told him, okay, I translated, but I totally disagree, and let me explain you why. So then we met with Steve and started talking with each other. And then a few hours later, we were best friends, and he invited me to the conference on inflation, where all three of us met half a year later in Cambridge.
For the first time?
This was, I actually should say that this was the second cosmology conference, but all three of us, cosmology on inflation, but all three of us have met for the first time at this conference organized by Steve Hawking in Cambridge.
So Stephen Hawking telling you that you were wrong in translation is the key point, the origin of the universe we're talking about right now.
Yeah. He thought that it should not work, but then, well, eventually he changed his mind, but he contributed to improving all this scenario. And then eventually he also, as many of us, after we met at the conference, we understood that my improvement of Alan's work actually is not perfect. And then for only a year later, I was able to improve it in the way which is the basis of well, many models of inflation right now. That's what I told you about chaotic inflation.
And how is it accepted now? I mean, what is the status of cosmic inflation in the 21st century astrophysics community? Alan, maybe you'd like to answer that.
Well, they just awarded us the Kavli Prize. It's hard to tell, really. It's certainly a subject for which the evidence for inflation has been mounting steadily for 30 years now, and there hasn't been any quantum transition along the way. So gradually, more and more people, I think, have become convinced that it's probably right. But I think there's still some doubts out there. And we're still waiting for better evidence, and we'll have to see what happens. But there's certainly enough evidence, so I think the three of us are pretty damn well convinced that it's the right scenario.
Yeah, and they can't take the prize away from you.
That's right.
As I understand it. But evidence like the cosmic, new images, like the very famous cosmic microwave background images, but also WMAP and things like that. All of that has helped build into this model, or have there been detractors along the way?
No real distractors. There are a few what are often called anomalies, things that don't seem quite right, but they're still at a low level of statistical significance, and it's not clear that any of them have to be taken seriously, although maybe we'll see. For the most part, everything has really just fallen beautifully with what inflation predicts. These measurements have narrowed down the possibilities for inflationary models, and that's important. Ultimately, we want to find one model that works, not many. And
what about the prediction of gravitational waves, which emerges at some point during the genesis of this idea? When are we going to see them?
Well, actually, this was the first thing Alyosha did back in '79 when he predicted that inflationary type models should give you gravitational waves. But that all depends on what is the level of the signal, because some of inflationary models predict pretty strong signal, which can be seen right now with, well, experimental abilities of astronomers at the moment. But some models predict such a small signal that you will never say never, but nevertheless, it's very, very difficult to observe. So if it is observed, it's great. If it is not observed, we have many, many models which suggest you just exactly that.
And the tools that we're using at the moment, like Planck and Bicep2, which are generating, they're in the process of generating their data. Do you have a steer? Do you have a guide on whether that is going to be positive or negative in terms of reinforcing the ideas as they stand?
If you're asking about this gravitational waves background, we really don't know. It's a very controversial issue. Whether, in particular, Bicep2 results will be confirmed. Probably they should be at least strongly modified, because most probably there is a source of the signal independent of this inflationary origin, which should be present there. But whether everything can be explained by this additional source, we do not know yet. And right now they are collaborating with each other, these two groups, trying to find out what is right.
That's right. Now, just to wrap up, I want to ask you a slight sort of fantasy question, but based on a real question, which is this. I want you to identify the really one big remaining question in cosmology that relates to your work. And secondly, with limitless budget, what is the experiment? What is the observation that you need in order to make that work? So maybe I'll ask you that first, Alexei. What is the big question in cosmology for you right now?
Well, much more speaking about inflation, because inflation is still not the whole cosmology. Inflation is the theory about something which occurred in the past, and another question: what is happening now, and what will happen in future? And this is another question about dark energy, about present dark energy. But speaking about cosmology, indeed, I would say that still a measurement, a final measurement of gravitational waves, and I'm sure that such effect exists. The only question is what is its amplitude. I would say that here the situation is completely similar to what we have in elementary particle physics, which predicted the Higgs boson, but the exact mass was not predicted. So it was almost there were some trivial sections. It was almost a free parameter. So I would say more or less we have the same situation with inflation. So we have definite prediction, but different, more concrete models, and depending on this information, it's very important information, which using this model, using this data, we shall be able to say much more about details of inflation. So much more about what happens both in the remote past of our universe, and even also much more about what happens in elementary particle physics at the energies more than about 10 orders of magnitude exceeding those energies which are accessible at the most powerful colliders.
Okay, Andrei, same question to you. What's the big driving question, and what would you do to answer it?
Well, I would say that we should add to this mix two things. First, the theory of inflationary multiverse, and the second is the in parallel development of theory of elementary particles. Because previously, for example, thinking about the way how the universe will end, okay? Well, we knew there are two ways for the universe to end. First, there is a cold death for all of us if the universe just expands forever. Second, hot death if it's closed universe, it collapses. And then string theory enters the game, and we are trying to join forces with them, and we are finding that every vacuum state, like the state where we live right now, will decay. That's a theorem assuming that the string theory is right. So when it decays, you have two choices. First choice is to die in the collapsing universe, and second choice is to transit to a 10-dimensional space and die there because planetary systems cannot exist there. But then, in addition to all of that, we learned that our universe eternally self-reproduces itself, which means that our part of the universe will probably die, but there will be billions and billions of babies producing more babies where new life will appear all the time. So what I'm trying to say that these developments were purely theoretical. Experimentalists are running, trying to follow, they are doing their stuff independently, but nevertheless they are guided in which direction they should go by development of theoretical cosmology. And theoretical cosmology is by many orders of magnitude more cheap than experiments which follow later. But the way it develops tells you something which we 30 years ago, we didn't have a clue that these questions actually are relevant and these perspectives are possible. And now if we continue doing this kind of stuff, just learning what is really possible, how to unify simultaneously the string theory, supergravity, theory of elementary particles from particle point of view, and our cosmological perspective. This is, I guess, the most promising direction.
Alan, have you got anything a little bit more positive that doesn't involve the heat or cold death of the universe that you're thinking about?
Okay, I guess I was not going to talk about I was not going to talk about the death of the universe, but actually I do want to follow up on ideas really which Andrei started to talk about. It seems that almost all inflationary models lead to the idea of a multiverse. Once inflation starts, in almost all of our models it never stops, but stops in places, and in the places where it stops, pocket universes form, and we would be living in one of these pocket universes. But the whole multiverse goes on producing pocket universes literally forever, as far as we can tell. That leads to some very interesting problems, which we still have not solved. And the key thing is that in a model like that, anything that's allowed at all by the laws of physics will ultimately happen an infinite number of times. And that poses a real problem when you want to talk about probabilities. You'd like to say that things that happen often are more probable than things that happen rarely, but if all those things are happening an infinite number of times anyway, it's hard to know what you mean by common and what you mean by rare. And so far we don't have a good answer to that question. We have at this stage a number of different proposals for how to define probabilities in this system, and many of those proposals work. Many also do not work, so there's interesting things going on in the study of these ideas. But we don't yet have any principle that really picks out what should be the right way of defining probabilities in these kinds of systems. So to me, that's the most important outstanding problem in trying to understand inflation.
And the neatness of that as a question means that there is a universe out there where you've already answered that question.
That's correct.
So you can be reassured by your theory is solved somewhere.
Unfortunately, it's difficult to travel there and to ask another Alan.
But that other Alan does know the answer already. But there's another universe where you've disagreed with them too. I'm going to stop this before it becomes too philosophical, but I just wanted to say thank you for your time and congratulations on taking the Kavli Astrophysics Prize for 2014.
Thank you.
Thank you very much.